next invited speaker, Professor Manu Jaiswal, and the speaker will present on knobs for tuning the physical properties of atom-thin graphene layers. And now let us listen to the biography of the speaker from Daniel.
Absolutely. So Professor Manu Jaiswal is a professor at the Department of Physics, IIT Madras, with current research interests in physics and applications of graphene and two-dimensional systems, and also on properties of water under confinement. He pursued Ph.D. from IISc Bangalore, followed by post-doctoral research at Max Planck Institute for Polymer Research at Mainz, and subsequently at NUS-Singapore, before joining IIT Madras in 2011. He is a recipient of the Young Faculty Recognition Award 2016 for Excellence in Teaching and Institute Research and Development Award 2019 for Excellence in Research, both from IIT Madras. He is an editorial board member of the Journal of Physics, Physics-D, Applied Physics, published by the Institute of Physics, UK.
Okay, thank you very much. So now let us welcome our invited speaker, Professor Manu Jaiswal, to give his presentation.
Thank you, Daniel, for the kind introduction, and thank you, Vijay, and all the organizers for extending this invitation. I'll share the slides now. Yes? Okay, then yes. I'll go ahead. Yeah, okay. So I'll discuss here about this wonder material called graphene and how its physical properties can be by different knobs, with some reference to its optical properties, given the interest of this conference on holography and such areas. So a quick overview of this. 1 minute. Graphene is a 2D crystal, and we'll see in particular what is the role of stacking order on its physical properties and effects on optical properties, what can be there. And I'll discuss about how such graphene can be synthesized. We'll also look at graphene oxide, which is a related system where there are defects present. And at the end, I'll touch upon what the implications could be for holographic imaging. That's not a field I work on, but given the theme of the conference, I have some message for holographic imaging. So let's see this. Graphene has a linear band structure. The crystal structure is shown here. It's a honeycomb lattice of carbon atoms forming one monolayer, and the electronic band structure is shown to the left, where you can see the conduction band and the valence band. At the corners of the Brillouin zone, the dispersion relation is quite unlike that of a semiconductor. A typical semiconductor has a parabolic dispersion relation, but in graphene, the special dispersion is that it is linear in nature. Therefore, the carriers are relativistic massless Dirac fermions, and this is the Hamiltonian at the Dirac point or the cable. What are the implications of this for optical properties? Graphene is having extremely strong interaction with light. A single layer of graphene is able to absorb about 2.3% of the light. And that is just a number, but the interesting thing is there are no material parameters whatsoever that appear in the optical absorption of graphene. It's just given by a fundamental constant, the fine structure constant. As you can see here, the absorption of graphene is pi e square upon h bar c, and which is consistently maintained across the wide wavelength interval. Reason, of course, is that there is a linear dispersion relation for electrons, and light also has a linear dispersion relation, leading to this special interaction. And this property has verified by transferring graphene to 10 grids, where every layer, every successive layer absorbs about 2.3% of the light. So is this something that can be tuned or modified is the question. And a lot of these things are available in one of my review article, but I'll just cite a couple of them. That gate is one means of changing the optical transmission, for instance, by using poly blocking or by shifting the Fermi level at different points of the band. And in particular, if they are shifted into or out of the Van Hoff singularities where there are large density of states, then for carbon nanotubes, optical windows which can be controlled with gate voltage have been made. But besides the use of gate, can we directly change the optical properties of graphene as a material? And the answer is yes, if we consider graphene with different kinds of stacking. I mentioned that every layer of graphene has a very definite absorption, which is given by the fine structure constant. And if you look at the stacking in graphite or in few layer graphene, then it is either AA stacking or AB stacking. In AA stacking, every layer, every atom is exactly on top of the lower atom of the lower layer. And in AB stacking, which is the most common type, the atoms are translated of one layer with respect to the bottom layer, such that only half the atoms, the A atoms, are on top of the B atoms. The remaining half are sitting on top of this void inside the honeycomb. These are the conventional stackings, but many interesting things are possible if one considers random stacking between layers. And this results in what is called as a Moire pattern, when two copies of periodic patterns are overlaid with a relative twist, as shown here for a square grid. These two square grids combine to give a new periodicity, as can be seen here. And in twisted bilayer graphene, one can take two graphene layers and give them some rotation, and that can result in a different periodicity. In general, there is no translational periodicity, but for certain commensurate angles, one can also have translational periodicity. I have lost the presentation. Sorry, gone to the end. Just excuse me. Yeah, sorry. Okay, yes. I hope it's still visible. I had just accidentally pressed the end stage. Yes, thank you. So if you look at the atomic structure for two kinds of rotation angles, a small twist angle of 5 degrees and a large twist angle of 21 degrees, then the unit cell in the real space, in this case, is very large, covers a large number of carbon atoms. And here it's relatively smaller. This means that small angles are associated with large periodicity in the real space, and the corresponding periodicity of the Brillouin zone is the opposite. That is, when there is large periodicity in the real space, the periodicity, the size of the Brillouin zone is extremely small, as indicated by these small black honeycombs. And the original size of graphene's Brillouin zone is depicted by the green and the orange hexagons, as shown here. So in literature, the typical methods one uses for making twisted graphene, one of them is a mechanical procedure where two layers are independently synthesized with chemical vapor deposition or by mechanical exfoliation, and then they are brought under certain rotation and brought in contact, and a desired angle can be created, as shown. Other technique involves direct chemical vapor deposition, where a new layer can be created. Say a graphene has grown on a copper substrate as a single layer. A second layer growth can be initiated on the step edge, and that would have a relative rotation. The carbon atoms would have the honeycomb would have a relative rotation with respect to the first layer, and this can result in twisted bilayer with different rotation angles. As a different approach, we looked at growing twisted graphene using a solid carbon precursor, and this is camphor, where at high temperatures, these methyl groups can be removed, and the remaining carbon ring rearranges to form large area graphene, and twisted graphene is seen to different degrees at different locations of these samples. We could image the formation of this twisted graphene using scanning tunneling microscopy. For instance, this is the STM image of HOPG, the conventional graphite, where one can see the triangular lattice corresponding to the AB stack structure. Only half the carbon atoms are visible. But in the case of this CVD grown twisted multilayer graphene, one can clearly see a moire pattern, and upon taking the FFT of this image, one can also measure. We found out that the twist angle between these layers was about 18 degrees. We have looked at different growth conditions, and not all growth conditions give this graphene with twisted angles. There are some growth conditions only giving Bernal graphene, but others can give statostatic with variety of twist angles at different locations. The formation of rotational stacking faults can directly be seen from electron diffraction patterns, where starting from a single sextet, one can go to multiple sextets, which indicates a large number of rotational stacking faults are present. But a direct indication of twisted nature is observed from Raman spectroscopy, where a large ratio between the 2D mode and the G mode is observed, where there is large twistedness, and this is directly attributable to the electronic decoupling of the graphene layers when they are under the twisted condition. The same can also be seen by looking at the line shape, because the Raman line shape originates from the electronic subbands which are involved in the Raman process. In graphite, there are many electronic subbands present, and that gives this characteristic hump shape. But in graphene, which is electronically decoupled or twisted graphene, even though the thickness is very large, a single Lorentzian can describe the entire Raman mode. So once more, we have a proof that this is possessing twisted layers. And then there are fingerprint rotational modes, or the R modes. And this is very interesting because Raman in graphene is only excited at the gamma point for the G mode, that is the zone center, or for a phonon process, it can be at the K point, the zone corner. But the inside of the entire Brillouin zone is inaccessible by Raman because the light cannot provide the momentum. But what interesting thing happens in twisted graphene is that the Raman condition can get satisfied all along the gamma K line, making the entire Brillouin zone accessible. And from the position of the Raman mode, one can infer the twist angle, as can be seen here. A variety of twist angles can be seen. The entire gamma K line can be probed, and twist angles from 10 degrees to all the way to highest possible 30 degrees can be achieved. What we studied in our research was how important this is for physical properties, and one property that we studied was the in-plane thermal conductivity. In graphene, it has among the highest possible thermal conductivities of all known materials, touching some few thousand watts per meter Kelvin, but add a tiny amount of twistedness and the thermal conductivity really drops down tremendously, whose effect can be understood that now there is zone folding, because the size of the Brillouin zone is changing tremendously. It has become very small, and because of zone folding and folded phonon branches, there is a lot of scattering happening. And this is what happens as a result of the twisted interface. In terms of its electronic band structure, some of the very subtle changes that happen are the following. This is depicted, the band structure is depicted for two layers. So this is one of the layers, and this is the Dirac point of that layer. This is the Dirac point of the adjacent layer, which is shifted in momentum, because these layers have a twist angle. And 1 and 3 denote three special points, because these are the Van Hoff singularities. 3 belongs to the monolayer, but 1 and 2 are special singularities which originate only due to the twisting. And as the twist angle is changed, this position of the Van Hoff singularities can be continuously tuned from one end to the other. That is, the point 1 moves closer to the Dirac point when the twist angle is 0. These two band structures get overlaid on top of each other, and 2 moves close to the midpoint, that is the M point, and 3 remains wherever it was. So Daniel, may I know how much time I have so I can plan? Sorry, I couldn't hear you.
No, it's okay. Sorry, you still have some time for questions.
Right.
But please.
Yes. Okay. Okay. So this is how the density of states varies for this twisted graphene. That is the Van Hoff singularities I described. They can be tuned continuously, and this depicts how the Van Hoff singularities varies as a function of the twist angle. This is for Van Hoff singularity labeled as 1, whereas the other Van Hoff singularity, which appears close to the mid of the K and K prime, that moves in the opposite direction. And this allows a continuous tunable optical property of graphene, which can be derived from this band structure. And shown here is the dynamical conductivity directly inferred from the twist, the change in the density of states. That the dynamical conductivity also possesses the same feature, which changes continuously with the energy, which means there is a clear knob available to modify the optical properties of graphene by changing the twist angle. A different route to modify the properties of graphene is to use defects. And in this case, we have extensively studied graphene oxide as a system. And here, for instance, if this is a cross-section depicting a single layer of graphene, and these are the carbon atoms, then in this cartoon diagram, you can see there are functional groups attached, such as this hydroxyl functional group or an epoxy functional group. And alongside that, this system can also possess interfacial water, which could be just a monolayer of water present between two sheets. One can know the fact that these functional groups are present, for instance, by doing FTIR measurements or by doing the XPS. And there is also a wide water-related peak, which indicates the presence of this interfacial water. This also is a different means to tune the optical properties. We had studied the variation of the complex refractive index as a function of wavelength using spectroscopic ellipsometry. And here one can see that refractive index, which this is the bottom curve for graphene oxide, continuously changes upon annealing and goes towards the refractive index of graphite, pristine graphite. As the functional groups are eliminated, by making an optical model, we could understand the changes associated with the refractive index are very gradual when the functional groups are eliminated, as given here. But over a narrow interval, this hatched region, the optical properties really change by a tremendous amount. That is, the refractive index and K both change by like a step function. And this we could identify is due to the expulsion of trapped water. Monolayers of water are trapped between, and once they are eliminated, the refractive index can become significantly different from what it was. Now, all this has important implications because graphene is proposed to be used as a material in various optical applications, and by using the stacking order or by using tunable defects or the intercalation of water are different means by which its optical properties can be modified. So I'll say the way forward here is that graphene has, as a conclusion, I'll say very unusual optical properties. For most systems, the optical properties possess some material parameter, which should appear in the transmission or reflection, but this optical property is completely given by only fundamental constants of nature, that is the fine structure constant, independent of material properties. But despite that, there can be more methods to tune its optical properties, and stacking order is one method I discussed, how that can modulate various physical properties, thermal properties or optical properties, and so on. And as a large area application, chemical vapor deposition is the route by which one can make graphene with various twisted angles. A completely different route modifying the optical properties relies on graphene oxide. And that has a tunable density and nature of the sp3 defects or oxygen-rich functional groups, whose elimination can change the optical properties. But at the same time, the more drastic change happens by the expulsion of water. In context of this conference, I would say that these are the main means by which the optical properties can be modified, but they can further be coupled with etching to obtain pattern graphene or femtosecond laser irradiation, which can create subwavelength structures whose refractive index can be modulated by using one of these possibilities, and that it could be useful for holographic imaging. So with that, I thank you for your attention, and I thank all the group members who have helped me in this work. So if there are questions, I would be happy to answer.
Yeah, thank you very much, Professor Manu Jaiswal, for your wonderful presentation on graphene. And recently, there have been many research works on making graphene lenses for imaging applications. And I think so there is a good research direction of graphene and holography together in the future.
Right.
So now, yes. So now let us see if there are any questions from the audience. Okay, so anything in the chat window? Okay, so if there are no further questions, so let us thank the invited speaker again for his valuable presentation. Thank you very much, Professor Manu Jaiswal. Yeah, thank you.